Welcome to the Explainer. Okay, I am absolutely pumped for this one because today we are diving headfirst into a mathematical mystery that has literally baffled experts for centuries. We are talking about a locked vault in the world of algebra that the greatest minds in history told us could never ever be opened. But a groundbreaking 2026 paper has just handed us the master key. Let's get into it. So this whole thing really starts with a very fundamental question. Can we find the exact solution to any math problem? You know, as humans, we just crave mathematical certainty. We want formulas that give us the perfect, unassailable answer every single time, no matter how complex the equation gets. But for hundreds of years, the highest levels of algebra have stubbornly refused to give us that certainty. Historically, that quest for certainty hit a massive brick wall right at the number 5. For centuries, finding an exact, general radical solution for polynomial equations of degree 5 or higher wasn't just considered difficult, it was considered mathematically impossible. The tools just didn't exist, and the absolute rules of algebra said it couldn't be done. But, well, what if those rules were just waiting for a completely new perspective? All right, here is our roadmap for today. First up, the high-degree polynomial problem. 2. Limits of classical math. 3. Introducing EMS's theorem. 4. The power of recurrence. 5. Conquering degree 8. And finally, number 6, a new algebraic paradigm.
Okay, let's jump right into part 1, the high-degree polynomial problem. Look at this timeline with me for a second. Back in the 1500s, Renaissance mathematicians were on a serious roll. They figured out exact algebraic solutions for quadratic, cubic, and even quartic equations. So that's polynomials up to the power of 4. But then, bam! Progress completely halted. It wasn't until the 1800s that math legends Galois and Abel came along, and they didn't even solve it. They actually proved that finding a general radical solution for degree 5 and higher was intrinsically impossible. And that right there remained the gospel truth until 2026, when the EMST framework finally shattered that exactness barrier.
Now, that 1800s proof, that's known as the Abel-Ruffini theorem. You can kind of think of it as the ultimate do not enter sign in algebra. It completely cemented the idea that higher degree polynomials were this unbreakable safe. Because of this theorem, mathematicians essentially threw their hands up, gave up on finding perfectly exact formulas for these high degree equations, and just turned to other, less perfect methods.
Which brings us nicely to part 2, limits of classical math.
So let's build a really sharp contrast between the old world and the new. Classical methods, like Newton's iterative method and the rational root theorem, well, they require an initial guess, and they frequently fail if the roots are complex. They only ever give you an approximate result. As the researchers note, traditional methods can carry an inherent error rate of roughly 30% simply because they aren't exact. But the EMST framework, actually, it requires 0 initial guesses. It handles complex, irrational, and repeated roots completely effortlessly. The result is 100% exact roots. No way, right? Let's formally meet the solution in part 3, introducing EMS's theorem.
Looking directly at this visual abstract from the source paper, the historical flow makes so much sense. We start with Girolamo Cardano and Isaac Newton's classical approximations, and then we take this massive leap forward to the EMST framework, introduced by Ezouidi, Murad Sultan, and Tawfiq Ghassoumi. We literally drop from that 30% error all the way down to a unified pathway with a perfect absolute 0% error.
So, how does it actually work? Let's get into part 4, the power of recurrence. The absolute master key to EMST is that it unlocks the polynomial from the inside, using its own genetic blueprint. Instead of externally guessing where a root might be on a graph, which is exactly what Newton's method does, EMST looks at the polynomial's coefficients. You know, those are the numbers attached to the variables. It treats those coefficients as the literal DNA of the equation, and uses recursive relationships between them to extract the roots directly. Now, the highly technical math in the paper is, well, it's pretty intense, but the logical flow is actually beautifully straightforward. Step 1, you just identify the coefficients of your polynomial. Step 2, you plug them right into the recursive EMST formula. And step 3, extract the exact roots. And the really crucial point here is that it doesn't matter if those roots are nice rational numbers, messy irrational numbers, or even complex numbers involving imaginary units. EMST finds them exactly, without any guessing whatsoever. Let's put this to the ultimate test in part 5, conquering degree 8. Just take a second to look at the sheer, staggering size of this 8th degree equation. X to the power of 8 minus 16x to the power of 7, plus this massive fraction of 724 over 8 squared x to the 6th, and it just keeps going. Traditional methods like the rational root theorem would completely collapse under the computational weight of this monster. The explosion in the number of candidate roots would just be prohibitive. But the researchers went ahead and applied the EMST recurrence formula to this exact equation. And the showdown results? An absolute victory for the new theorem. EMST extracted 100% exact, closed-form roots from that massive 8th degree behemoth. It completely bypassed all the limitations of rational roots, easily identifying the complex roots. And in this case, we're talking about roots involving the square roots of negative numbers and imaginary units. And honestly, most importantly, because the method is recursive, it scales infinitely. It doesn't just tap out at degree 8. It works for degree 18, degree 80, or literally any polynomial degree you throw at it.
Which leads us to our final takeaway, part 6, a new algebraic paradigm.
I really want you to read this powerful quote directly from the researchers' paper. They state, "The EMST-based methodology offers a unified pathway toward exact solutions for long-standing algebraic problems." Listen, this isn't just a neat little trick for one specific type of math problem. It is a unified pathway. Polynomial equations are foundational in control theory, in physics, and in engineering. By proving that we can actually extract exact roots without approximations, a centuries-old locked door has finally been blown wide open. Which leaves us with this final, thrilling question to ponder. If the impossible Abel-Ruffini limit, a rule that's been taught as absolute algebraic law since the 1800s, can be entirely bypassed with a new recursive perspective, what other unbreakable scientific boundaries are just waiting to fall next? It is such a great reminder that in science and math, impossible sometimes just means we haven't found the right blueprint yet. Stay curious, keep questioning the impossible, and I'll catch you on the next explainer.